and Associate Dean.
Thank you very much. I'm very honored to be here. John asked me to come and give this presentation on behalf of Richard Hay. I was very pleased to do so. He sent me a set of slides, or probably 80 or 90 slides. I cut it back by half at least. And I tried to make time for some videos of wax modeling. And so thanks to Doug Oldenburg and Jim Brune, we went ahead and made some new hybrid models of the wax modeling, which have also been further developed by some people at Cornell, and we'll show some videos of the work they've done. Okay, so this is set to go. Here it is. I'm ready to go. Oh, one last thing before we start. I'd like to point out that Marty Kleinrock and David Kress both tried to make it here as well, but they couldn't make it. So, and Mike Healy was also part of our Tectonics lab back then. And so, as Doug had mentioned, people who help us along our way, I'd like to acknowledge here. As mentioned, Bruce Leinbach, Anya, and Ken and Steve played an instrumental role as an undergraduate at Santa Barbara. The first time I went to sea was with Bruce, and the first time I took an oceanography course was with Tanya Atwater, which was her first course being taught at UC Santa Barbara. I also want to thank Richard Hay, of course, for bringing me here to Scripps, and my committee members, Bill and Harmon and John Orcutt. And I have to give a special thanks to Bob Parker and Jim Brune, who were very supportive during my time here at Scripps. And I continued work with David Sandwell, and thanks for John Slater's invitation. And also, keeping in touch with your alumni is very important, and I've been working with Jeff Gee and others in the past. Now this just jumped, so that's good. I guess it's keeping me on time. Now, I did a quick Google search to see how many publications have been published in plate tectonics, and I came up with something shy of 500,000 publications, 130,000 for seafloor spreading, and I got to stop hitting this button. And then there is about a little less than 20,000 publications on propagating ribs. I thought this was an interesting discovery for me. And then Richard Hay noticed these magnetic isochrons, the 1961 Raff Mason survey in the Northeast Pacific off the west coast of the U.S. It wasn't until the year before, it's a very sensitive button here. Okay, the year before, in 1968, 7 years later, Fred Vine took the magnetic stripes and the seafloor spreading hypothesis and provided a colored version of these magnetic anomalies, showing the symmetrical pattern and the anomaly patterns of these magnetic stripes. And this will become important a little bit later down the road. So in the early 70s, Richard Hay went to the Galapagos, working on his PhD, looking at the three plate motions of the Nazca, Pacific, and Cocos plate, working with Jason Morgan, and in the process of looking at the triple junction evolution, he also noticed some interesting patterns along the Galapagos spreading ridge. He was looking at magnetic anomalies, and remember, on an east-west spreading center at the equator, the magnetic anomalies are going to be upside down, so the normal polarity will be a negative anomaly. And we noticed that the 3 million year isochrons were completely linear and straight, but at the zero ridge axis, there was an offset. So something caused the ridge to reorient into a new location. Now, if you look at a schematic mid-ocean ridge model, where you have simply two plates pulling apart and you have uprising of the asthenosphere, it makes sense that the spreading would continue at the mid-ocean ridge. So the question was, why would the seafloor spreading stop at the mid-ocean ridge and jump over into an area which is thicker lithosphere? Peter Vogt compiled a series of magnetic anomalies around the Galapagos spreading center. North is to our left, so this is looking off towards the east. And there was a series of anomalies that are correlated with blue and red lines. And I swear to God, I didn't even touch the button. I must be touching my computer. And so there was a pattern here, if I can, of disrupted magnetic anomalies that seemed to get further away from the ridge as you went further to the east. So Hay looked at the magnetic anomalies for each of these profiles, the observed anomalies are on top, and below are a synthetic model, and we found that a rift jump would have to occur for each of these anomalies. And so he recorded these rift jumps and the time and the location that they jumped, and plotted the distance along the spreading center of these jumps. The left plot is the time of the jump. In the middle plot, it's the distance of the jump. And then the very far right plot shows the distance of the jump with respect to the time of the jump. And all three of these plots show a systematic pattern of rift jumps. And he realized that this must imply that the spreading center and the transform fault itself is migrating towards the west. And the way he envisioned this to occur is that at time 0 you have a ridge, transform ridge, and then all of a sudden the rift propagation goes to the south and brings the transform fault with it. And the old spreading center and the old transform fault fracture zone gets left behind. And then spreading occurs and creates this new green material here, and a new jump occurs. And you can keep repeating this process until you get to stage 3. And you can see the staircase pattern of left behind transform faults on either side, and a failed rift on this side. Now, this is a discontinuous model. If you made these steps in a sequence, there are two things here you want to notice. One is that this spreading center is not parallel to the previous one. And so one thought was that these spreading jumps is a way for the ocean ridge to reorganize its orientation, and so doing increasing the length of the transform fault over time. If you take each of these steps of the propagation and make it continuous while making each individual step very small, we get this continuous pattern that Hay proposed for propagating rifts. Now, it wasn't clear. I apologize, I don't know why this is jumping so much. But it was clear that these anomalies in this transferred zone where the lithosphere would transfer from one plate to the other had this oblique orientation for magnetic anomalies, and this dashed line would be the failed rift. And back in the beginning, it was all together, and then the transform fault got bigger and bigger, which represents the width of this triangle. So taking this model and going back to Juan de Fuca, Richard Hay, along with Doug Wilson at the University of Hawaii, put together a model. This is the outcome of the model. You go back one step. They digitized the Rafa-Mason model and created this situation, and then they allowed the ridges to propagate in different orientations at different speeds, and came up with this model, and it looks pretty similar to the original data. Now, this was a large area looking at the magnetic anomalies. And what was noticed both in Juan de Fuca and the Galapagos is that the spreading center was actually an area where the spreading center would change orientation. Now, it's been found that propagating rifts don't always change the orientation, and they propagate parallel to the previous ridge. In response to the original question of why do rifts jump, there's something that initiates it where the jump wasn't into a large area of lithosphere, but once it continues breaking into a thicker lithosphere. But it's a gradual process. Shortly after this project, Menard and Richard Hay had a proposal put in to test a project that looked at how changes of magnetic anomaly orientations occur. One was a Z pattern that Tanya Atwater and Bill Menard proposed that showed the ridges would reorient by looking at asymmetric spreading. In part B, they showed what it would look like with rift propagation. David Kress and Marty Kleinrock, Richard Hay and Bill Menard went out to sea and tested this place between the Farallon change in plate motion around anomaly 23 and onward. Now, as we talked about fun things you do in the lab and how you integrate with your other students, we had a fun time putting tables together for some of the papers that was being published. And so we had a good time testing these equations and making sure they worked out right. And looking at the magnetic anomaly data collected at Galapagos, it was found that this continuous model worked pretty well, but the magnetic anomaly patterns weren't as clear-cut as the previous model would predict. This implied to Hay that maybe there was some kind of overlap where the spreading would pick up slowly and the failing rift would die out slowly. So there was some kind of simple shear that was required. And so he had this model proposed of what a distributed shear model would look like. So instead of having an instantaneous transform fault, you had a distributed shear zone. To test this, Roger Searle was also going by with the Gloria side-scan sonar system, and they noticed that the abyssal hill fabric seemed to run straight through east-west. There was no evidence of north-south transform faults as one would expect. So they proposed that the isochrones and the abyssal hill fabric should be sheared by the orientation by this angle beta. And so they went to sea to check this, but before they did, they had a bookshelf model which would imply that the abyssal hill fabric would be rotated such that the right lateral shear would form left lateral shear along the edges of these abyssal hill faults. This is a picture of Hay from Ken McDonald on one of the cruises they were on. And this is the outcome of the survey. The very deep propagating rift tip from the western directed propagating rift. You can see a V-shaped pattern of the pseudofaults. And the ultimate test of this hypothesis of this bookshelf faulting was the curved abyssal hill fabric. And this curved abyssal hill fabric showed that it wasn't an instantaneous transform fault forming. They went to punchline. But it was actually abyssal hill fabric being rotated. And of course, Richard Hay always loved to send his work to others for comments and ideas. And he sent this to Dan McKenzie. I don't know if Dan, you remember this. But Dan's response to looking at this image was a bunch of equations. And those equations were defining these curved isochrones, failed rift pattern, and he had a complete set of descriptions of these patterns. And I believe he did this within a week or so, or less. Now, the distributed shear model would predict that the earthquakes would be occurring throughout that region. In fact, ocean bottom seismometer survey that Fred Dunbeer did during one of these surveys showed that the earthquake distribution pattern was widespread. And initially, they had assumed that it would occur up in here where the tip was cracking through the old lithosphere, but in fact, most of the deformation was occurring here. At this time, Marty Kleinrock was at sea with during these surveys and produced 3 papers as a graduate student. This is a bar for the rest of the students here to maintain. First paper was about the tip cracking through. This is from data collected on a deep toe study. Then he looked at the study of the transform shear zone, looking at different models for this abyssal hill fabric rotation. And the third paper was how the failed rift fails. And of course, if you have this type of deformation in a broad zone or transform shear, you would expect the seafloor to be full of talus, and in fact it was. And so, in summary of the Galapagos propagating system, there was a broad zone transform shear, and these are the components of what it looked like. Now, looking at the different models that were proposed for a propagating rift, the top 2 were not observed, but the bottom one was with this broad zone of transform shear. And these types of patterns, the number C, is mostly observed everywhere else that we've seen propagating rift studies. Now, going to wax modeling, that's David Sandwell on the far left of the camera taking pictures at the University of Hawaii. Above him is Marty Kleinrock, Richard Hay, and Brian Taylor. And when we built this tank here at Scripps, we got this funded by an NSF, it was an ONR proposal. The paddles were so heavy that they caused the bar that was pulling the paddles to bend, so we drilled holes through like ping pong balls through the paddle to make it lighter. And the wax solidified around these paddles. When this is a box that was formed at the Scripps, but we took it to Hawaii and it's still there. And I believe Oldenburg's box is at UC Santa Barbara now, is my understanding. And the box on the far right was built in the USF in 1990, and these boxes are much larger than the original box. They're about the size of 4 feet by 6 feet on the lower right-hand corner. And these are some students that were involved in a project we were doing. Now, it's 6 feet by 4 feet, about 6 inches thick, a lot of wax. And I just want to mention this now before I forget. The reason some of these wax experiments didn't work is that Eberhard Bodenschatz discovered that Shell changed the formula for the Shell 200 wax. It used to be made from petroleum, but they decided to make it a synthetic wax, and it lost that tensile property that allowed the seafloor spreading pattern to occur on the wax. So I found 3 last remaining slabs. I brought one of them here with me to this meeting to provide to Doug's, because it's going to be a collector's item soon, because they don't make it anymore. Okay, moving on. I'll be showing videos from those wax modeling experiments at the very end. So what if the overlap scale is huge? So the propagating rip model works on scales of tens of kilometers. But Hay was interested in the Eastern microplate. This is him supporting me as a grad student. And looking at the data along the Eastern microplate, they had structures and earthquake seismology. These were earthquakes relocated by Engel and Stein. And it showed a very circular pattern once I merged all the bathymetry data that was collected by the Germans and the French and our surveys. And we found a very deep hole in the north called Peto Deep. Sarah Muller is going to be providing a poster at 5 o'clock today. We'll talk more about this area in a minute. Later this afternoon. And so the circular pattern of the Eastern microplate shows that it is not a propagating rip pattern that you would expect that we saw at 95 West. Looking at the side scan sonar collected by Roger Searle in 1988 showed a similar pattern of this curvature. The dark backscatter represents young volcanic rock, strong backscatter. And the light areas are areas that are probably older and sedimented. As you can see, it's a very complicated series of abyssal hill patterns. And this is a picture of Richard Hay on the left, Roger Searle in the middle, and Jean Francheteau on the right. Jean was very instrumental in inviting me on these projects, and one area that was most interest was the Peto Deep area. And he wanted to look at this deep hole. It's about 6 kilometers deep, and there's which is in these cool colors, and there's a Peto Seamount. You can almost see a abyssal hill fracturing right through the center of this volcano. And you can learn more about this area at the poster that we can give. From that Latino survey, we went back in 2005 with Jeff Carson, and more recently 2017 with Jeff E. and many others. They had better control on crustal structure, and more smokers, black smokers, were discovered on this Peto Seamount, which I discovered back in 1993. So in summary of the larger version of a propagating rift system, it comes to a point where instead of having shear and transform shear, a plate starts to form and becomes a rigid volume. And it turns out from the magnetic analysis I did and the inversions I did with the Minster and Jordan routine, we found that there's a pole rotation very near the eastern propagating rift and another one close to the western propagating rift. Hans Schouten from Woods Hole and others propose this model. It's an edge-driven microplate model in which plate A moving to the right and plate B moving to the left captures the microplate like a ball bearing between 2 pieces of wood and rotates. And as it rotates, rifts start to propagate to fill in the void as the plates separate. So this is a different kind of rift propagation resulting from this rotation. Gary Acton showed a table trying to discern where we go from shear to rigid behavior. And so in the lower left-hand corner, we looked at some simple propagators and overlapping spreading centers that Lonsdale and Ken McDonald have been looking at in the early 80s. And to try to look at the, I don't know why this keeps jumping, I'm not touching anything. So looking at this larger overlapping spreading center, find a place that looks like it goes from transform shear to rigid behavior. There's a rift propagating southward from the eastern microplate, and looking at the Gloria backscatter data, there's clear evidence that it's overlapping in dual volcanic activity. And Coronaga and Hay modeled this, and the ultimate result was the patterns that were observed on the seafloor suggest that this plate area is now starting to behave like a rigid plate. And so Hay would place the boundary for the rigid shear area somewhere in this region, about 1.5 to 2 times 10 to the 4 kilometers squared. And of course, Peter Lonsdale one time ago mentioned that the South Pacific is probably like a quilt work of microplates, and a paper by Eakins and Lonsdale show this pattern very nicely on the right-hand side here. Here's the Easter plate, the Juan Fernandez, Bauer is up in here, the Mendoza and Mendana. And it's clear that these propagating rifts and microplates play an important role, especially at these faster spreading rates. And another place where propagating rifts play a role is in simple triple junction evolution. If you have a ridge triple junction, like Mackenzie and Parker pointed out, in any case, the triple junction stability required that these rifts would propagate, and the rough smooth boundary of this triple junction here and here is somewhat of a pseudofault of the optical spreading center trying to fill in the void. Now, in the title of my talk, I mentioned propagating rifts from back arc basins to continental breakup. And so here's some examples. A recent paper, well not that recent, 2008, the Philippine Basin that was being discussed earlier by Dan Carrick. And there's evidence of propagating rift evidence there. It's been also observed in Fiji. What is doing this? Fiji Basin, Lao Basin, and Philippine Basin. So we have a continental breakup. Here's the Red Sea, and I don't know, maybe this thing's on an automatic timer. I think that's what's probably going on. In any case, that's the Red Sea and the Gulf of Aden, and there's a paper by Vengeni right here. Showing dual overlapping propagation in the Gulf of Aden in the Par region, showing the actual geology and the volcanic activity associated with that. And of course, Baker in 1982 proposed this continental breakup model, and as the rift would propagate up the page, the longer it propagated, the more you have deformations. So when you close these continents back up, you would expect to have a lot more overlap. And so when you look at the Bullard fit of 1965, where you have gaps and overlaps, the Bink model would predict all this area to either to be touching or have some overlap, because you would have to undo all the normal faulting that occurred during the deformation process of the continental rift. And so we're now at the Iceland area. Richard Hay always had a great fascination with Iceland, especially these V-shaped patterns south of Iceland, which he interprets to be propagating rift wakes. A very recent paper by Martinez and Hay in 2017 showed that this propagation occurs to the south, but there are actual dueling propagation events that go right back up to the north. And this process is still a mystery to why these things duel back and forth like that. And then finally, the paper also proposes a new buoyant mantle propagation model, but that's outside the scope of this time. So in summary, before I go into the videos of the wax modeling, propagating rifts are extensional plate boundaries that gradually break through the disparate plates. They occur over a wide range of scales in various tectonic settings with various driving mechanisms. Propagation and spreading combine to produce characteristic V-shaped wedges of lithosphere. And rift propagation is the primary mechanism that reorganizes Earth accretionary plate boundary geometry. And as the title pointed out, these propagating rifts are throughout the different oceans, triple junctions, hotspots, microplates, and back arc basins, and play a role in continental breakup. Now, one of the other places they play an important role is Tanya Atwater's talk she'll be giving tomorrow about the continental breakup in California and the borderland area. No, I'm not going to talk about that. I saw it in the title. In any case, I took it out of my talk because I thought you were. In any case, Richard Hay had two different papers and models for the breakup of the Baja California and the borderland area using propagating rifts as well. Okay, so I'm going to go to the close this escape, I guess. thanks to Doug's introduction to wax modeling, I won't spend too much time describing what's happening. Bottom line is we just melt the wax until it's completely liquid, then we let it freeze. It freezes from the top down. And we have paddles put into the liquid wax while it's freezing, and then we can pull the paddles apart, and the liquid below comes up and attaches to the trailing edge. This top image here on the left, I don't have to worry about changing slides now, is a seafloor spreading pattern with transform faults, another spreading pattern, and more transform faults, and these are fracture zones off to the left. This thing here was an attempt to create a hot spot in the wax model. I don't know if you knew we did this, but we put a heat probe below, and as the heat rose up buoyantly, it would melt the wax that had just been formed. And we wanted to see, if you imagine we're in the northern Pacific looking towards Antarctica, what would happen as the spreading range approached the Easter hotspot. And this was just a quick model that we did. So this video is 2 minutes. And how much time do I have? Perfect. So this is moving forward now. Let's make sure. Yeah, I'm going to make this larger. So as you can see here, the spreading range is moving to the left, and this is the little hotspot location, melting the wax above. And we're trying to see what happens as this ridge approaches. If you remember the Easter microplate picture we showed before, we had evidence that near Easter Island, rip propagated northward. And so the anticipation here is that something might crack through and propagate northward. And sure enough, to the right here, this is turning off and slowing down, and this propagates south. And so this was a very exciting thing. I turned off the volume because we're all screaming and yelling and all that. Okay, the other one is a short model, that Richard Katz and Eberhard Bohnschatz, the people I mentioned, discovered that shell wax and changed their formula. Used a different kind of wax because it couldn't get the older to work. And I'm going to make this larger so you can see this. This only lasts about 10 seconds, so I'll do it again. So what they showed in this model is that they did it with a different kind of wax that was slower, and they sped up the video. But what we have here are transform fault, and fracture zone. It's kind of a zone of deformation, and Bird and Naar back in the 90s proposed that microplates might start and originate in these transform fault zones. If you watch carefully, you can see the little microplates spinning up in these transform faults. And so they seem to be edge-driven, like Hans Schouten predicted, and not so much something propagating in the center of the ridge. And this was an exciting find. And then the last thing is an example when there are no transform faults, it's just microplates galore. And I will show that, and I'll be done. That won't allow me to make it larger until I finish it. There we go. So these are ridges that are propagating towards each other, and like Ken McDonald likes to propose, these overlapping spreading centers on a very small geospecific rise to the size of microplates are all very similar in their behavior to some degree. I'll show this one last time, and then I will be ready for the discussion. And so you can see these microplates seem to initiate new microplates, and which might explain the pattern we see in the South Pacific, as you pointed out, Peter, a long time ago. Okay, that's it. Thank you.